Hello everyone, welcome back to Learning Hub and welcome back to hands-on machine learning with PyTorch. So in the previous video, we implemented a simple linear regression model using just a single feature, the area of house, to predict its price. So if you haven't seen that video yet, go check it out using the link at the top of this video. So in today's tutorial, we're stepping up our game by working with many features or multiple features. We'll build a more powerful model today that uses features like area, number of rooms, and maybe number of floors to predict house prices. So without any delay, we'll dive right in. First of all, we'll import our required libraries and then we'll load our data set. And we'll take a look at a few rows using df.head. So this will help us verify that all the columns are correctly labeled and present and loaded in our data set. So yeah, if we see here, we see column like area, rooms and floors, and then the corresponding price. So area, rooms and floors will be our feature variable, whereas price will be our target variable. To better understand the relationship between our feature and target variable, we'll use this Seaborn's library pairplot function. So what it does is it creates a scatter plot between all pairs of columns and histograms for like each individual features, which will help us in identifying any strong correlations or maybe locating outliers visually. So let's run this. And now we'll take a closer look at this pair plot. So if you're new to machine learning or data science, this might seem a bit overwhelming at first to you, but let me break it down for you step by step. So a pair plot is basically a grid of plots that let you visually explore the relationship between every pair of features in the dataset, including the target variable. So if you now see this plot, we have all the features in the x-axis along with the target variable, and the same thing in the y-axis as well. So first of all, we'll try to focus on these diagonal plots here. These diagonal plots are one for each individual feature. So what these show is they show histograms to show how each and every features are present in our data set. So for example, we see a bell-shaped curve here, right? So a bell-shaped curve shows a normal distribution for us. So understanding the spread of each feature helps us understanding whether scaling is required or not. So the other plots that you see that are not on the diagonal are basically scatter plots. So each one show how two variables are correlated to each other. In our area versus price plot, we see an upward trend here, right? So basically we see that dots moving from the lower left to the upper right here. That suggests a positive correlation, which means higher the area, the greater the price is going to be. So these kind of visual analysis is basically super useful when we train a ML model. It helps us understand which features might be more predictive of the target and like whether you need to transform any data or not. So in our case, we can clearly see that area and price are strongly correlated, which makes sense. Basically, bigger house generally cost more, right? So features like rooms and floors may also show moderate correlationship or like a moderate positive relationship with the price. We separate the features and target variables. So X contains our independent variables, basically the area, rooms and floors, and then the Y contains the dependent variable, which is the price. So let me run this. So to make the training more stable and efficient, so we basically normalize both the input feature and then the target variable using StandardScaler. We did this in the previous video too. If you haven't checked that out, I'll again keep the link up there. So please go and check that video out once so that you understand it properly. Basically what StandardScaler does is it ensures that all the features basically have a mean of 0 and a standard deviation of 1. So like without normalization, features like area if you see in our dataset, can go up to a range of 3000 or 4000, and they could dominate some smaller ones, or like smaller features like rooms and number of floors. So let me run this part too. After that, we split our data into training and validation set. So what this will do, this will help us evaluate how well our model is performing on unseen data. After that, we convert our NumPy arrays into PyTorch tensors, which are the fundamental data structures used by Python during any model training. So let me run this. Now it's time to define our ML model here. So this is a bit complicated than the previous video. So in PyTorch, we build models by creating a class that inherits the nn.Module package, which is a base class for all neural network model in PyTorch. So think of this like creating as your own neural network. So inside the class, the first method that we have is the init method. This particular method acts like a constructor. So it runs once when the model is created, and then we declare an element and sets up all the building blocks the model will need. So the line super inside this init function simply calls the constructor of the parent class nn.Module, so that all internal machinery get initialized properly. Then we start defining our layers. So this is our first fully connected layer, which takes in 3 input features: area, number of rooms and floors, and produce 16 different outputs or neurons here. After that, we add an activation function, which is ReLU. So ReLU stands for rectified linear unit, and it introduces non-linearity to our model. So without non-linearity, no matter how many layers we stack, the model would simply behave like a linear model. So non-linearity helps us in converging our result as a part of our efficient model. So next, we again stack a second dense layer where the input features are 16, which was produced by the previous layer, and then the output features are 8, which is again followed by ReLU. And then since we're doing a regression task, so at last we have a final layer which takes in 8 input features and then 1 output features. Then we move on to the forward function. So this is where the actual computation happens when you pass the data into the model here. Think of this like as a method, as a flow of data through the layers. The input first goes to the linear layer 1, passes through the ReLU, then goes to linear layout 2, passes through ReLU, and then finally goes to the output layer. So this structure is typically also known as a feed-forward neural network design. So why did we add so much depth to our model rather than including just one simple linear layer here? So while you can use just like one simple layer for like a simple task, what adding depth does is it makes the model more powerful. So as long as we have enough data and proper regularization, these model helps us in achieving great result. Also, using multiple layers and activations helps the model learn complex patterns in the data, especially when the relationship between the input and the output are non-linear here. So if you see the graph again, we do not see a linear relationship between the price and then any other features here. So for such non-linear relationship, these multiple layers and activation functions play a great role in achieving a better result. So we then create an instance of our model, and then we define a loss function, which is the mean squared error loss, which is kind of standard for like regression problems, and then we choose Adam optimizer for efficient training here. So now we move on to training the model part, where we loop for 300 epochs, make predictions on the training set, calculate the loss, backpropagate the gradients, and then update the weight here. And also in every 50 epochs we print the loss to monitor our progress. So let's do this. Okay, as you can see, as the number of epoch increases, the loss is kind of reducing. Well, the model could be trained for furthermore epochs, because we might not have reached the efficient loss yet. So let me increase the number of epochs to 1000. Let me reinitialize from the model part. So we see that we've gone quite far down, but the model had started saturating at around 0.06. So no further training should be required, because we have very small amount of data, so we might face a problem for overfitting here. So now we can move on to the evaluation part. So after training, we evaluate the model using the validation set here, where we calculate the mean square error to check our performance. Then we reverse the normalization so we can compare the actual and predicted price in the real world terms. So we'll print out a few examples so you can see how closely the model's prediction are to the actual values. So as you can see, the actual values for the first prediction was 532,000. The model predicted 508,000. Well, it's okay. We'll have some loss here. So the model will not be 100% accurate. For the second prediction, there was a difference of around 30,000. For the third prediction, there was a difference again of around 30,000. For the fourth prediction, the difference was around 40,000 somewhere, and then in the fifth prediction it was again around 30,000. So we could assume a deviation of plus minus 30,000 in terms of the prediction for this particular model here. So here we'll also create a helper function to make predictions in our new data. We can pass values like area, rooms, and floors, and the function handles all the pre-processing, prediction, as well as the post-processing step. So finally, we can test our function with a sample house, where the area is of 3,000 square foot, which has 5 rooms and 2 floors, and then we can print the predicted price. So let's see what price it shows. So the price it shows is around 392,760. So let's see. For 3,000 square foot, 5 rooms and 2 floors. 3,000 square foot, which is similar to this one, 5 rooms and 2 floors, it shows 392,000, which is close to about the range of price that we have in our data set. So this is it. This is how we can include multiple features in our data set. But when using multiple features, please be careful to analyze the data set and basically observe the spread of our data, and then maybe you can analyze some form of trends in the data. Also, never forget to normalize your data set, because the range of the values that you might have in the data set would be might not be same. So you always need to normalize your data set. We talked about a very deep model here. It would work better if the amount of data was huge, but since it is a small data set, so the result that we've got is also satisfactory here. So this is it for this video. I hope you could also implement the same following this particular tutorial. So if you have any confusion, do comment down below and I'll try to help you out. In the next video, we'll come up with something new and interesting and fun. So until then, stay tuned. I'll see you in the next video.